Switcheroo! In this lesson, we are going to extend our understanding of the first fundamental theorem of calculus and apply it to finding the area between two curves. We are going to introduce the basics of these type of problems. We are going to go through 4 examples, which I feel go from easier to more difficult. The last one is going to involve a little bit of trigonometry and some understanding of odd functions, which will hopefully allow us to kind of shorten the process of finding the final answer. All these problems have been written to be solvable without the aid of a calculator, but if you are given problems that do require the use of calculators, we'll throw a little video in the middle of helping you understand how to do that with your calculator, finding the intersection of 2 graphs and doing a numerical integration with your calculator. Okay, so the 4 examples, you'll find timestamps in the description of this video if you want to skip ahead and just get to those examples. But for the basic introduction, let me get out of the way because I did use up the whole board here to make sure I can fit my 3 diagrams. If f and g are continuous on the closed interval of ab, and if g of x is less than f of x for all x in the closed interval, then the area of the region bounded by the graphs of f and g and the vertical lines of x equals a and x equals b is, our area is equal to the definite integral from a to b of f of x minus g of x d of x, or dx. With respect, we're integrating with respect to x because that's our independent variable the way this formula is written. So what I have up here is 3 diagrams to illustrate to you that it doesn't matter if the functions are above or below the x-axis. We should have understood from our work with application problems, maybe working with the first fundamental theorem of calculus, that if a function falls below the x-axis, then all of those sums are going to be negative. And we can't have a negative area. So, you might go, okay, well, this saying here, okay, I have a closed interval from a to b, and we have our function f of x is always greater than g of x, like our theorem here requires. And we're going to, just like when we first were introduced to estimating area with a finite number of rectangles, which then moved into a limit process, which then moved into the first fundamental theorem of calculus, we have a little rectangle, a representative rectangle here, which we would be using, an infinite number of these to estimate the area. And the height is found by doing, f of x minus g of x, and the width is dx or delta x. Well, these are both above the x-axis, so it would kind of, with our understanding of that first fundamental theorem of calculus, say, okay, well, if I found the area bound between the function f of x and the x-axis on the closed interval of a to b, I would have all of this area shaded in all the way down to the x-axis. And then if I just found the area bound between g of x and the x-axis, I would just subtract that, which kind of looks like exactly what this theorem says, or this rule says for us to find the area bound between 2 curves. Well, now, we have g of x is below the x-axis, and over here, I've got g of x, I've pushed them down so that they both function f and function g are below the x-axis. And when we only had one curve, again, when that curve fell below the x-axis, we understood that those sums became negative, which was okay for some application problems, like maybe velocity where you have a positive negative movement, but not for area. Well, remember, we're just finding the area of a bunch of rectangles, which is width times height. So as long as the width and the height stay positive, of course, we're going to have a positive area. And I'm kind of just making up some numbers here. Let's just say, for instance, for this function f and this function g at c, that our y values, our values coming out of our function, are 8 and 3. Well, that's going to give this particular rectangle at a value of c the height of 5. And so that would be some kind of width times height, and that would give us an area for that rectangle. Well, if I push both of those functions down by 4, and again, I almost wrote this as f of 2 and g of 2. I just want to show you that I'm pushing these down 4 units, and so the distance between these functions would stay the same. Well, 8 minus 4 is 4, and 3 minus 4 is negative 1, and still doing that f of x minus g of x idea with a sort of like certainly not a proof, but just a concrete example, we have 4 minus negative 1, that y value 4 from f of x, and that y value, this idea of this y value of negative 1 from g of x, well, 4 minus negative 1 is still going to give us a height of 5. So that rectangle will still have the same width, and at least at the value of c, trying to match all these graphs up, we have a height of 5, and thus we can see that the area would still be positive between these two graphs, as long as f of x is always greater than g of x. And indeed, if I push them both below the x-axis with a vertical shift of down 10 on both of the original functions of f and g of x, well, 8 minus 10 is negative 2, and positive 3 minus 10 is negative 7, and negative 2 minus a negative 7 is still that height for that rectangle giving us the same value of 5. So as you find these areas between two curves, again, the restriction here is they have to be continuous on the closed interval, f of x must be greater than g of x on that entire closed interval, and if it is, the area is, again, the definite integral from a to b of f of x minus g of x dx. And it doesn't matter if one or both of those functions are below the x-axis. Bam! Now, the previous page said that our area which we were finding between two curves was bound by the vertical line of x equals a and x equals b, which is a requirement if the functions never intersect. And it can still be a requirement if the functions intersect, but a lot of questions simply say find the area between intersecting curves, and thus you have to find where those two curves intersect because they are going to define the lower and upper limits of our definite integral. So, guess what you have to do? Find the intersection points. That'll either be algebraically or with the aid of a calculator, depending on the difficulty of the problem and the requirements that your teacher is asking of you. And then it's going to be the area is equal to the definite integral from a to b of f of x minus g of x dx. Now, let me just talk a little bit here about why is the x values of my 2 points, my intersection points, defining the lower and upper limits of my definite integral, because that's not always going to be the case. Usually, but not always. If you look at this notation, we're taking an x in and plugging it into function f and finding, well, if it's f of x, we're finding a y. So it's the y values of the functions that are defining the height of the rectangle, and then therefore the width of the rectangle is defined as dx or delta x. So we're using the x values, the horizontally, right, the values along this horizontal axis to define the lower and upper limits of our definite integral, because the y values of the functions, if you will, are allowing us to find the height of the rectangle. So if you want to find the area and let the x values determine the lower and upper limits, you're going to be doing that when you are talking about functions which are in terms of x, and those functions giving us a y value which we are subtracting. Or you could say, if you're using vertical rectangles, then you're finding the area along the horizontal distance, a defined value, or that's defining our closed interval. Okay, well, if we have functions which intersect more than just twice, and thus they're going to set up multiple areas which we have to find the area of and then add up all those pieces, well, in this graph we have function g of x is greater than function f of x between the intersection points of AE and BF. So, okay, we'll find the area of that portion, or that area bound by the intersecting graphs by doing the area is equal to the definite integral from a to b of g of x minus f of x dx. Again, using vertical rectangles and having the widths defined as delta x. We'll be integrating with respect to x. But after we get to the right of this intersection point, the function f of x now becomes greater than function g of x. So we're going to have to find this area where it's g of x minus f of x, find the area bound between these intersecting curves, which is going to be f of x minus g of x, since function f is greater, and that will be the area of the first region plus the area found by doing the definite integral from b to c of f of x minus g of x dx. Now in this third diagram, this is going to be one of those more difficult problems we get to as an example. I've got, just to have something to look at to explain why this would be so difficult to find the area where we're going to find, use a bunch of vertical rectangles. We have a sideways parabola, if you will. G of x is equal to plus or minus the square root of x minus 1 plus 3. And then another unknown function here of f of x. If you're going to find this area with a bunch of infinite vertical rectangles, we have an intersection point here. We'll just go ahead and call that BC. And we have another, let's call that BE. And now we have another intersection point over here, which we're going to call CF. And this previous page and these first two examples, we found the function that was on top, the greater than function, and subtracted it with the function that was lower or less than, right? Well, if I come down here and draw a vertical line, and that's going to be, the vertical line is going to be x equals b, then this side's pretty obvious. Function f is greater than function g of x. Now it's plus or minus the square roots of x minus 1 plus 3. So that means that we have what we would, with a parabola, be calling this the vertex, and we're going to label this as point A, G. Well, then we're talking about the lower half. So this would be something like f of x minus negative square root of x minus 1 plus 3. But then what do you do over here? Because it's sort of like, this parabola, it's its own upper and lower values. So you would have to, sort of account for a horizontal line going through here. And we would be subtracting this function, which is the square root of x minus 1 plus 3, and subtracting it with this part of the function, which is negative square root of x minus 1 plus 3. So let me get out of the way, erase this board, and show you what it would look like. Now I'm not giving you function f, we're going to do that in great detail with the third example, I think it is, we're going to do. But let me just clear this off and show you a little bit of idea of what algebraically would look like to find that area if you're going to use vertical rectangles and integrate with respect to x. So, if, again, this is a relatively simple example with this just being a sideways opening parabola, I'm able to, with this concrete example, find this vertex, and if you know your vertex form or standard form of parabolas, then this would be the x-coordinate of the vertex, which is 1, and the y-coordinate is equal to 3. So this point is 1, 3. Now, again, we would find this area here by doing, the area is equal to the definite integral from 1, that's the x value of this vertex, going to the upper limit of b, and this area would be found by, this y value is the square root of x minus 1 plus 3 minus these y values down here, which is negative square root of x plus 1 minus 1 plus 3. And so this first part of the equation would find this area. And then the second part, like I said, that's a bit more straightforward. That would be the definite integral from b to c, what I have labeled as my two x values here, my intersection points, of f of x minus, now, this, the way it's drawn, f of x is above the bottom half of my parabola, so minus negative square root of x minus 1 plus 3. Well, that's rather complicated, and finding the integrals may possibly be not very simple. So if I would rather use, let's see, another colored piece of chalk, if I would rather use horizontal rectangles, then I would be, instead of having the widths defined as dx, my widths would be defined as dy. Now, if I'm using horizontal rectangles with a width of dy or delta x, then it's going to be my y values that define my lower and upper limits. So I need to turn these graphs around, these equations around, and not have them in terms of x, but having them in terms of y. So that would mean for this one, I would subtract both sides by 3. Then I would square both sides of the equation. And I would start to run out of room. I would then add 1 to both sides. And write that function in terms of y. I would have some kind of x function now in terms of y, and then this would have to be rewritten also to be in terms of y. So I'm just going to write like an f of 2 and have it like in terms of, so showing like I don't know what the function is, but turn the values around and solve for x so I would have some kind of function in terms of y. Now that would be a lot less work because I still have my intersection points, which we would have to find first, but as you read, where I have my large, well, for any particular value of y, it's my larger x value, right? So I have these larger x's, and then, right, because if I plug in a y into a function, I'd be getting out what? An x. So I have these larger x's, and then I have these smaller y's, so I'll be doing this function, which is f of x, minus this function over here with these smaller x's for each respective value of y that we'd be plugging into the function. And we would have a simpler definite integral to estimate or find that area between those two intersecting curves. That would be the area is equal to the definite integral. The lower y value here is f, and the upper one is e, so it would be the definite integral from from f to e, of, again, that reading that from right to left where I have larger x's and then smaller x's, f sub 2 of y minus, maybe I should be calling it g sub 2 of y, but I gave us a concrete equation for that one, so it would be minus y minus 3 cubed plus 1. And again, we're integrating with respect to y. So it's this kind of this function here that as we do our third example, we're not going to want to find the area with a bunch of vertical rectangles because it's going to really complicate the process. We'll find them with horizontal ones instead and have some simpler work. As long as you can write these functions that are given to you, turn them around and have it sort of like an x in terms of y, you can do that easier. So let's get on to the first example. I think, no. I'm going to go on to actually give some formal language on how to do these rectangles horizontally. Putting into a formal statement what we just did in our former sort of end of that sort of non-example example, horizontal representative rectangles, because it didn't really give you both functions. Reversing the rules of x and y. If w and v are continuous functions, and if w of y is greater than or equal to v of y, for all y in the closed interval from c to d, then the area of the region bounded on the left by x is equal to v of y. And I'm just looking to make sure I have this drawn correctly. And on the right, by x is equal to wy, below by y is equal to c, and above by y equals d, then that area is found by the definite integral from c to d of wy minus v of y with respect to y, or dy. So we have, again, this, it doesn't have to be, of course, a sideways parabola, but we have function v, we have function wy, and that's just the diagram that goes along with this statement, again, using those horizontal representative rectangles. And we'll know they're horizontal representative rectangles if we were integrating with respect to y. Okay, now, before we move on to our concrete examples, the ones with all those numbers in them and real functions, you know, this particular example looks kind of like the other one, and whether you find it easier to find the area bound by this actually three functions here with vertical representative rectangles or horizontal ones is really just going to depend on the functions, because if you want to use horizontal rectangles, then there's still a dividing line here where we're going to be doing, you know, I mean, these are, well, you can see that these are in terms of x, so we'd have to turn all those around, but it would be something where we're taking the y values, or what would it be? I guess f of y, if you will, f sub 2 of y, taking these values here and subtracting it with this function for this lower bound, and then this orange graph, or f sub 2 of y, if you will, minus g sub 2 of y, where you had to turn both of those functions around. But the point is, you would still have to set up two definite integrals, whether you were finding this area with horizontal representative rectangles or vertical ones. Because if you want to find them, if you want to find the area bound by these functions using vertical rectangles, which is sort of how my notation is set up, of course, with my independent variables of x, then you're still going to have to use two definite integrals. So that would be, with the way this is drawn, the area is equal to the definite integral from, after finding the intersection points, from c to a of the greater function is g of x minus h of x dx plus this area over here, definite integral of e to c of the greater function is f of x minus, again, h of x. So unlike the last sort of example we started talking about that led us into these horizontal representative rectangles, some kind of diagram like this, horizontally, vertically, you would still need to find the area with two definite integrals. And again, however you decide to do that's going to be determined on how the functions are set up, as opposed to graphically or with the number of definite integration expressions we need to set up. All right, let's get on to some actual examples. Sketch the region bound by the graphs of the algebraic functions and find the area of the region. The functions are y is equal to negative 2/3 x times x minus 3, y is equal to negative 1/2 x plus 11, x equals 0, and x equals 6. Why do you need to sketch the picture that these are, the graphs that these functions are forming? Because, it looks like they gave us a couple of vertical lines, so it seems like this should just be our lower and upper limits, but what function is above the other one? Like, what is the greater function? Do they intersect on that closed interval where we're going to find the area, and thus requiring us to set up two integration expressions as opposed to just one? So let's get out of the way. You can pause the video and do this on your own. Let's find out what this function is going to look like. That's, of course, obviously just going to be a line, and allow that graph to help us set up the definite integral. So we, of course, took the negative 2/3 x, distributed it through the parentheses. I noticed that it was a parabola, which you can put into standard form or vertex form, whatever your textbook calls it, or I found the x of the vertex doing negative b over 2a, getting an x coordinate of the vertex of 3 and a y coordinate from that 3 of 6. And I didn't really have to find the x-intercepts really, because we already have our left boundary of x equals 0 and x equals 6, but the parabola is opening down, and they have the x-intercepts going at 0 and 6. So this would be, I think, much simpler, clearly, if we find the area using vertical representative rectangles, and thus our area is going to be found by the definite integral from 0 to 6 of, now, you know, we've written the rule, it said it was f of x minus g of x, but with, oh, by the way, I relabeled these functions because I didn't want to just have like two y's, have the same name for two different functions in the same problem. That's an issue. And the way I had it labeled, I inadvertently put g of x on top as the greater function, which is perfectly fine. So that straight line, that g of x was negative 1/2 x plus 11 minus the other function, our downward opening parabola of, you just might as well use this one, negative 2/3 x squared plus 4x dx. So let's get this out of the way. Hopefully by now we're very comfortable finding, and evaluating definite integrals. So I'm going to pull out, move this green chalkboard out of the way, and reveal the answer one step at a time. If you want to practice your integration skills, just pause the video and try it on your own first before, I give you the answer. So hopefully you found that one to be pretty straightforward. Negative times a negative is positive 2/3 x squared. Negative times 4x is negative 4x, and negative 4 plus a negative 1/2 comes out to be negative 9/2x plus 11. This is just a basic polynomial here, so raising that power by 1 and then dividing, we get 2/9. Raising that power by 1 and getting x squared, we get 9/4. And then finally 11x as we find the integral with respect to x, and then finish up by plugging in, doing this function with the x substituted in, minus our lower limit of 0, and we get an area of 33 square units. Okay, next example is going to involve a couple of slightly more complex polynomials, and they're going to intersect a couple of times, or a few times actually, setting up two areas, which we'll need to find each individual area and add those results for a final answer. With the same directions, we have the functions of negative 4x plus y is equal to 12 and y is equal to x cubed plus 3x squared. And we're not given any vertical or horizontal lines to finish, bounding the area. So we're looking for the area formed by the intersection of these two graphs. I went ahead and sketched the cubic graph for us, and what basically is just a line, 4x plus 12. Hopefully, maybe you'll have this diagram already given to you, or you have the ability to use a calculator to help you graph that cubic function. Otherwise, you're going to have to find x and y intercepts, and remember all those steps we had to go through for graphing polynomial functions. At any rate, we do need to find the intersection points so we know how we're going to set up the definite integrals. Now, if you look at the way this function curves around, think about what you would have to do if you were using horizontal representative rectangles, where the if you were doing it horizontally, the greater bound and the lower bound are made with the same function. That is going to be very, very difficult to try and figure out. So this would be a much easier problem to do with vertical representative rectangles again. So we're going to find these intersection points and then allow the x-coordinates of those to set up the lower and upper limits of our definite integrals. So, grab some chalk here. We're going to set these equations equal to each other and find those intercepts. Now again, I'm trying to make some problems that I can relatively easily do on camera. So this will be solvable without the aid of a calculator. And not stumble too much around trying to get this done for our example in our video. So we have this equation, these two parts set equal to each other. We're going to move everything to one side and set it equal to 0. And solving these higher order polynomials, well, you could be talking about having to find a long list of possible rational zeros and doing synthetic division until you get a remainder of 0, and then keep doing that process until you get down to a second degree, and you can finish with the quadratic formula. If you have the ability to use a calculator in your class, of course you can graph that and find the zeros or the roots or the x-intercepts graphically with your calculator using some kind of calculation command in the graphical menu. Or, hopefully, about as easy as these can get, is if they're factorable by grouping, which I said I was trying to do these so that we can go through them relatively cleanly, and this will factor by grouping. So, what comes out of these first two terms? They both have a common factor of x squared. X cubed divided by x squared is x, and then plus 3. We can take out a common factor of negative 4 from these last two. And now we have two terms that both have a common factor of x plus 3, so we can take that out. And then last step here, we still have a factor that is factorable again, and that is a difference of two perfect squares. And that's going to give us zeros of x is equal to negative 3, x is equal to negative 2, and then x is equal to positive 2. And since we are going to find or estimate or find the area bound by these two functions using vertical representative rectangles, this is all we need to set up the lower and upper limits of those definite integrals. But as I move out of the screen and clean all this up, I will go ahead and give us those full coordinates of those points just to let you know what they are. With room to work and our intersection points identified, we're going to go ahead and set up that definite integral. So we have again this first area. So we are going to find the area by setting up the definite integral of our lower limit is 3 and our upper limit is negative 3 and our upper limit is negative 2. And that will be of this function on top is g, so x cubed plus 3x squared minus, and if you want to wrap that entire polynomial or function up just to emphasize that substitution, that's a good idea, but it's not going to do much except for this minus sign here. If we don't distribute that through the second function, we're going to have sign errors and get the wrong answer. In this first area, the lower function is f of x, so we have 4x plus 12. And of course, we're integrating with respect to x. Don't forget that dx. That's the first area. Now moving on to the second one, we're going to, with that, add the definite integral. Lower limit's negative 2 and the upper limit is positive 2 of our upper function, our greater function is f of x now, so it's going to be 4x plus 12 minus our lower function is x cubed plus 3x, or x cubed plus 3x squared. Now, these are pretty straightforward polynomials, and we've been doing integration now for quite a while, so I'm going to go ahead and move out of the way and reveal this in small steps. And again, pause the video and try it on your own if you like, but I'm not going to go through every single one of these steps very slowly. Bam! 131 over 4 square units. After you take the area of these two regions and add them up. Now, clearly, this was easily solved by hand and was even a pretty basic polynomial for us to do our integration with, just to use the power rule. If you couldn't find these intersection points by hand, or if the functions did not, fall into, or we couldn't use some of our fundamental integration rules to, integrate these functions, then you would have a situation where you would have to use a calculator to find these intersection points and the area of these regions so that you could then add them up and get our answer. So, even though we could do that this problem by hand, I'm going to, just before I get on to the third example, throw in a little clip of how to do this with a calculator. CAS, and I'm going to do this the same way so you could manage it with a TI-83 or TI-84. We're going to go to Scratchpad, get the graphing up. We already have the entry window open. One of our graphs was 4x plus 12. Hit enter. Hit the tab button again to open up that entry line, and we have x cubed, arrow over to get to the exponent, plus 3x squared. Enter. Alright, well I can't see the intersection of these two graphs. So I'm going to go to Menu, go to Window Zoom, and do window settings. We're just going to close up that window a little bit, maybe -7, and I'll X max of +7. And we went low enough. Let's let the Y max be 24. There we go. Now I'm not going to find both of these areas. If you understand how to do one, you can do both. So let's find this bigger area here. Now we're going to find the area below the linear function and between the intersection points of -2 and +2, and then we're going to do the same thing with the cubic function and subtract them. So we're going to need to first find the intersection points, assuming we don't already have those. So we're going to go to Menu, Analyze Graph, find the intersection. Calculator will ask you for the lower and upper bound. I'm using my touchpad, of course, but you'll be using this pad here on your calculator. And there's our intersection of -2, 4. And then finally, again, Menu, Analyze Graph, arrow, use the touchpad, go to intersection, lower bound, upper bound, and then there are other intersection point of 220. Alright, so I want to find the area below the linear function of 4x plus 12 between these values. Menu, Analyze Graph, let's find the integral. The calculator will ask you what graph. We want to do this one, so you have to do this one graph at a time. Lower bound, you can just type in the number. So I'm going to go -2, and there's a little box opening up here. Enter, and you'll see that it's actually, with the Inspire, will show me the area below the curve as I move my upper bound around, but we want that set to a concrete value of 2. So I'm going to enter, just hit 2. There's a little window opening up for me, and we had that area of 48, and I'm writing that down on my piece of paper. Now we're going to find the area below the cubic function. So again, Menu, Analyze Graph, Integral, which graph? Well, I want to use the cubic one this time. Lower bound, again -2. Oh, and I'm using my keyboard, but you would be good at hitting negative here, 2. And enter, locking that up. Did I get that? Yes. Okay, upper bound, then I want to again have that be a value of 2. So just hit 2 and enter. And that lower area, or the area below the cubic function, between that and the x-axis was 16. And if you subtract those, 48 minus 16 is an area of 32, which was almost the complete answer, I believe, between the area of those two graphs, because this is such a small area. Now this is a CAS version, which stands for Computer Algebra System. I could come over here to the, well, you'd probably hitting the tab button here, but to toggle between the two views, I can go to Menu, Calculus, the integral. My lower bound again was -2. My upper bound was +2. And here I can just get the answer of 32, hopefully get the same answer, and I can actually just type in the subtraction of those two functions. Now, again, the linear function was first, which was 4x plus 12, minus, and then the other function has a lot of terms in it, so I'm going to use parentheses. That cubic function was x cubed plus 3x squared. And we're going to integrate that with respect to x. And voila, we have the answer of 32 again. Now that was just one of the two areas. You have to find the other one with a similar fashion and add those two together to get the same answer that I got in my video. Alright, so thank you for watching. Let's get on to the next example. Third example, same directions. Let's find the area bound by these two graphs. Again, we have a straight line. Okay. So, and here we have y squared is equal to 2x plus 10. So, we have clearly what is a parabola, and the y is squared instead of the x, so it is opening sideways. Kind of sounds familiar to something I talked about earlier in this video. That means that we have y squared is equal to 2 times x plus 5. So our vertex here is at negative 5, 0, since this is already in standard form. So negative 5, 0, we got one right there. We have, if we let x equal 0, we're going to have 2 times 5 is 10, and then y squared is equal to 10, so y is equal to plus or minus the square root of 10, which is, a little bit more than 3, so our x and y intercepts are just a hair greater and smaller than 3, and our parabola opening sideways looks something like this. Kinda. And then we have this line of y is equal to x plus 1. Well, that clearly just has a y-intercept of 1 and a slope of 1. So this isn't really graph paper, so I'm just trying to estimate where all these little tick marks are. And so we're looking for this area here. Well, I've already discussed in this video that why I would not want to find or do a problem like this with vertical representative rectangles, because in this area here, I'm going to have to do sort of that plus, well, first of all, I have to find the vertex, but it was only a parabola, so not too big of a deal there, we already did. But finding that area right here to the left of that line is going to be complicated. So we're going to do this problem with horizontal representative rectangles. So we're going to be basically using stuff like this. Sort of, right? With a dy. So that means that we need to get these functions rewritten so that they're x in terms of y. So here we've got, well, that's not going to be too hard, right? We're going to need to rewrite this function as x is equal to y minus 1, and we can call that g of x, or g of y, excuse me, is equal to y minus 1. And then for our function here, we can take this, subtract both sides by 10 and get 2x is equal to y squared minus 10, and then divide both sides by 2, giving us x is equal to 1/2 y squared minus 10. And let's go ahead and call that f of y. Okay, so now I have my two functions in terms of y, which will allow me to set up my definite integral expressions, and be able to integrate them with respect to y. But what are we going to use as our lower and upper limits? Well, we're going to take these functions, and really it doesn't make any difference what format you look at them in, but we do need to set these equations equal to 0, or equal to themselves, and solve those out. And I don't think we need too much help solving systems of equations, so let me step out and reveal that solution one step at a time. Alright, well, you saw what I did, substitution method. Took that value of x from really this first equation, plug it into the second one, and solve for y, and got y is equal to 4 and negative 2, which means our intersection points, not that we really need to know the x's because we're going to integrate with respect to y, but they're negative 3, 2 and positive 3, 4. Well, let's go find out why the dogs are barking. Alright, now that my little watchdog here has made sure that we're safe, let's go ahead and finish up by setting up this definite integral. Come on, guard the house. Alright. So we have, as we rise from our low y values to our high y values, and I look at what's bounding our area here on the right side and the left side, this is our greater x values and our lower x values, then this is going to be the area is equal to the definite integral from our lower limit of -2 to 4. And what are we subtracting? Well, again, the farthest right function giving us the greatest x values, that's that straight line of, with the independent variable of y, it's going to be y minus 1 minus, which I call g of y, minus our function on the left side with the lower x values in this bound area of, I'm going to go ahead and take this -1/2 and distribute it through and get, how about we call it y 1/2 y squared minus 5. And again, find that integral with respect to y. And we should by now have tons of practice finding indefinite or definite integrals. So again, I'm going to go out and reveal this one step at a time. If you want to try it on your own, of course, just pause the video and work out your answer before you see mine. So our area comes out to be 18 square units. If you wanted to check this answer with a calculator, and I don't know how to do numerical integration with a calculator unless it is with respect to x. If anyone knows any other methods, maybe drop me a line and give me a hint on how to do that. But if I wanted to find this area with a calculator, I would have to get that parabola written so it would be y in terms of x, and you would have to, I don't know if you can see all these different colors here, you would have to find the area of this region, bound between the parabola and the x-axis, the area of this region, which is only a triangle, so that wouldn't be too terribly hard to figure out. Then you would have to find, that would be for the areas below the x-axis, and make sure that you wouldn't have like negative areas. Then you would have to find the area of this region and of course we'd have to find out what that value is there and have the lower and upper boundaries of -5 and -1 for that particular case. And then find the area of this one, where you would have to find the area bound between the parabola and the x-axis, between -1 and, ooh, bad spacing there, 3, and then subtract it with the area bound between the straight line and the x-axis to find that final answer. So it'd be quite a bit of work to find the same answer of approximately 18 with the aid of a calculator, because you'd have to get it all in terms of y, in terms of x, and then find all those little pieces individually. So at any rate, at least that's how I would think about doing the problem. I got one more example dealing with trigonometric functions and odd functions. Hope you're finding this helpful. Last example. Same thing, find the area bound by the functions, and we're only given 2 functions, and we have a closed interval. So, let's see if these functions intersect. Maybe one function's above the other one on the entire closed interval. I don't know. Don't know unless we have a graph, right? So, hopefully remember, graphing some basic trig functions. If not, at least I'll help a little bit here. We've got a sine function whose only transformation is an amplitude of 2. So instead of going like the sine of 0 is 0 and the sine of pi over 2 is 1, well, the sine of pi over 2 is 1, so 2 sine of pi over 2 is going to be positive 2. And we have a tangent function who's got a vertical stretch of a value of square root of 2. So basically, we know that hopefully that the tangent of 0, the tangent is y over x, and so the tangent of 0 is 0 over 1, which is 0, and the tangent of pi over 4 is square root of 2 over 2 over square root of 2 over 2, or 1, right? So the tangent of pi over 4 is 1. Well, now with that amplitude change there, if you will, that vertical stretch value of square root of 2, it'll be square root of 2 instead of 1. So let's just get a quick sketch. Now the tangent function has asymptotes. There's no horizontal transformation. There's no left to right phase shift. So it's still going to be centered around the origin. There's also no vertical shift. So the standard period of tangent is pi, but the y-axis, if you will, takes that first period and sort of splits it in half. So we're going to go to negative pi over 2, and roughly try to make this equal positive pi over 2. And the tangent of pi over 2 is y over x. X is 0, so it's undefined. Thus we have our vertical asymptotes, or at least 2 of an infinite number of vertical asymptotes. And then we know from my class last year that if you want to graph trig functions using or getting the simplest values as possible, you count by 1/4 the period, and 1/4 of a standard period of pi is pi over 4. So the tangent of 0 is 0. The tangent of pi over 4 is normally 1, but now it's going to be square root of 2 here with that a value of square root of 2, and I'm just going to put that here. And that means that our function is going to look something like this. Make that point bigger so I actually hit it. And the tangent function is going to come down through pi over 4 square root of 2, come through 0, 0, and of course, hopefully you remember some of your properties of your trig functions. The tangent function, barring the fact that it's been shifted left to right or up or down off of that origin, is an odd function. So it's going to look something like that. Probably made the spacing out a little bit too big. But it kind of swings down and sort of makes this S shape through the origin. Okay. Now, the tangent function, or the sine function, at least within that area that we have there, the sine of 0 is 0, and 0 times 2 is 2. The sine of pi over 4 is a bit of a nasty problem, but I do know, or question, but I do know that the sine of pi over 2 is equal to 1, and now it's going to be multiplied by 2. So the sine function is going to look something, maybe something like this. Cross through, and then the sine at negative pi over 2 is negative 1, but nope, now it's negative 2. And, very rough sketch I'm drawing here, but, so I apologize for my sloppiness. We are going to need to find the area of these two regions. Now, are those really intersecting at pi over 4 and negative pi over 4, or is there a bit of a gap? Does it fall a little bit shy, or does the intersection point a little bit to the right of pi over 4, and thus the sort of orientation of the graphs flip-flop? Because here, the sine function is above the tangent function. If the intersection point is before pi over 4, then they're going to switch orientation, and we're going to have to do another integral with the subtraction reversed so that we don't get, any kind of negative area. So, while I have a drawing done, you could see it was a very rough sketch. I'm kind of making it look like the intersection points are happening at those x values of negative pi over 4 and positive pi over 4, but we really do not know that. All we know is that on this side in quadrant 1 for a while, the sine is above the tangent, and in quadrant 4, we have that the tangent, or the tangent function is above the sine function. So let's work on finding those intersection points. Well, that means that we're going to have to set these equal to 0, or actually, set them equal to themselves. It will become, I'm going to change it so it is set equal to 0. Okay, we have an equation with two variables. You can't solve an equation usually when there's two variables in it. Certainly we're not going to be able to do anything here with us having a sine function and a tangent function. So I'm going to do two things. I'm going to move this term over to the left, and I'm also going to write it in terms of sine and cosine. Okay, now when you're talking about your algebraic functions, and maybe there's something more complicated that I don't have off the top of my head, or we haven't dealt with really at the level of math we're at, often, or one of the rare cases where we can solve an equation when there's two variables in it at the same time is if they factor apart. And indeed, both of these terms have a factor of sine. And there's a cosine function too. So we still, again, have two variables in the same one equation. But the sine, if we take that out, we get the sine of x times 2 minus the square root of 2 over cosine of x is equal to 0. So now we factored our two, now our two variables are in two separate factors, which is good because, after you factor an equation, of course, you set each one equal to 0, and voila, our two variables are now in two separate equations. This video is a little bit long, and I don't know if you really need to see me talk through every step of solving these individual equations for x. So let me step out and reveal those answers and get this graph out of our way. Alright, solving each one of those little equations, we have x is equal to 0, and we have x values of negative pi over 4 and positive pi over 4. So the author here, or I wasn't trying to trick you, this is my problem, but it's inspired by a textbook problem. So I'm not trying to trick you too much. We have an intersection point here at 0, 0, and the graphs intersect at the lower and upper limits of our closed interval. So, before we finish this up, now, and get to the main meat of this problem where we find the area, this, again, tangent functions, assuming again you haven't moved it left and right or up and down so that you ruin that symmetry that it has, but in its sort of parent form, we just have a change of amplitude, if you will, here, even though tangent really doesn't have a true amplitude, it goes up and down forever. But this is an odd function. If you plug in two odd numbers like negative pi over 2 and positive pi over 2, you get opposite answers. This is an odd function. Well, the sine function, again, barring any issues with phase shifts or vertical shifts, this is just still sort of centered around the origin, if you will, except for that amplitude change. It's an odd function as well. So since both of these are odd functions, we can find just one of these areas and multiply it by 2. So as I get all this, I'm going to move out, get all this cleaned up, I'm going to set up a definite integral from 0 to pi over 4, but I'm just going to do from 0 to pi over 4 and then multiply it by 2 so that we don't have to find the area of this region where the tangent function is above the sine function and then turn around and find this region where the sine function is above the tangent function. And just find 1 and multiply it by 2. So, recognizing these times when we have even and odd functions can save you some work on your problems. Just can't forget all those things you learned in Algebra 2 and Pre-Calc. Alright, we got our definite integral set up. It is for that area in quadrant 1, multiplied it by 2 again to account for the one in quadrant 3 that will be equal in area. I'm going to write this separately and have this as 2 times the definite integral of 0 to pi over 4 times 2 sine x minus 2 times the definite integral of 0 to pi over 4 of square root of 2 tangent of x. And I just realized that I forgot my dx in there. Don't do that. Your teacher will probably mark off a couple of points. Now, I'm going to, in the next line, take the 2 and move it out front. We know the integral of sine is negative cosine of x. That dx there, now I've just slipped right in there. I'm going to bring this 2 out front. Now, if you remember the integral of tangent, great. If you don't remember the integral of tangent, like I'm going to write this as sine over x, or sine of x over cosine of x, just to walk you through an extra step if you need to, because you forgot the integration rule for tangent. But you really need to start working on memorizing those integration rules for standardized for your test, or maybe the AP exam coming up in probably a few months if you're watching this video right now. So this is going to be 4 times the definite integral of 0 to pi over 4 of sine x, let's get that dx in there now, minus 2 square root of 2 times the definite integral from 0 to pi over 4. Now if we write that sine of x, or that tangent of x, as sine of x over cosine of x dx, we can recognize, hopefully, an integration rule that will help us finish this problem up. See, if we let u be our denominator, remember that pattern of integrating u prime over u? If we let u equal cosine of x, the derivative of cosine is negative sign, but we have a positive sign up front. So if we introduce a negative here, and then bring a negative 1 out front, sort of effectively multiplying by negative 1 and dividing by negative 1, I'm going to change the look of this integral expression, but not its value. And now we have the pattern of u prime over u. Whoops, excuse me, over u, which the integral of u prime over u is some sort of natural log function. So at this point, hopefully, you're starting to see how to finish the problem up. So again, I'm going to step out just to speed things up a little bit and show you the solution step by step. Bam! Well, maybe. You might have done all this work and got to this answer. Go to the back of the book or look at the multiple choice options you have on a test and realize it doesn't match. Okay, if you're doing your homework, did you really do it right? Well, you could plug it all into your calculator and see if you get the same decimal approximation of what's in the back of the book. If you're taking a test and you don't have access to a calculator, that's not going to help. Or, again, with the multiple choice test, not getting that in the same format as one of their choices. So this is done, and unless I made a mistake, it's all correct. But how can we change the look of this to, again, possibly match what's in the back of the book, maybe actually what came out of my TI Nspire CAS with the computer algebra system, or choices on a multiple choice test? Well, we have all these properties that we can use to expand log functions or expressions. And I can rewrite this as negative 2 square root of 2 plus 4 plus 2 square root of 2 times the natural log of 2 to the 1/2 power divided by 2 to the first. Now when you divide like bases, 2 to the 1/2 power, of course, is square root of 2. When you divide like bases, you subtract the exponent. So 2 to the 1/2 power over 2 is 2 to the negative 1/2 power. Or I'm like unrationalizing the denominator here. Alright, well, when you take the log of something that has its own exponent, the power property allows you to take that exponent and pull it out front. Well, when you do that, you're going to have negative 1/2 times positive 2. Well, half of 2 is equal to 1, and you bring the negative down, and you have a final answer of negative 2 square root of 2 plus 4 minus, from that negative times positive, and the 2 divided by 2 is 1, so you get minus square root of 2, natural log of 2. Now that might be the answer that you see in a multiple choice test in your back of the book, and yours was right as well. If it's an AP exam and it's an open-ended response, you don't get points for simplifying your answer, so maybe that's acceptable. I don't know, but I hope what I have shown you is enough to get through your homework. So, I'm Mr. True. Bam! Go do that homework.